is 20 kilograms. Got 20 kilograms, 5 kilograms, 6 kilograms around the pulley.
Okay, so the other day we started this one. Then there was some questions that I asked already. If I allow this to accelerate, what's going to be the acceleration of these guys? And then we said that 20 kilogram is going to go back. It ends up that this one becomes a pretty complex problem. Almost to the point where it's like an extra credit, maybe extra credit. Because what ends up happening, this one goes to the left. This one swings outward, and then it creates an angle. Then you got this one pushing out, this one pushing in. So I tried to work it. I said, you know what, let's leave this as extra credit option. So this part B, however, is more doable. Part B said, if I exert a force F here, right? What was the question? If I exert a force F, what should I exert the force? How much force should I exert so that these two stay in place? Something like that, right? So what's going to happen then if I exert a force, this is going to accelerate forward, right? This tends to swing this way down, to the left, okay? So if we assume that the block is kind of large, so it doesn't swing too much, so this block can be 4 kilograms, and let's say it's kind of large, so even though it swings, let's just say the string remains vertical. Then it becomes an easier problem to do, right? So then you don't have to worry about that, the angle of the tension. Okay, so then this one accelerates forward, right, with an acceleration A1. Okay, now if you want this not to accelerate down or up, it's just going to stay in place, right? So what's going to happen? Well, there's a force in between this and this. Naturally, they're going to be touching each other, right? So this guy is going to exert a force on the 20 kilogram back this way. We can call that any symbol like P, let's say, right? And then the 20 kilogram is going to exert the same force on that guy, that way, P. So that's an action-reaction pair, right? So this one tends to swing this way when I accelerate this guy. Exerts a force back. This guy exerts a force on that one. Then you got the tension in the string. But if it's not accelerating down, then whatever the weight is, 4 times 9.8, that's 39.2, right? The tension in the string, therefore, is equal to 39.2 because the 4 kilogram does not accelerate down, right? So part B then, we're doing T is equal to 39.2 newtons. Okay, what are the forces on this guy? You got the 20 kilogram exerting the force on it, N, right? And then you got its weight, which is 5 times 9.8, which is 49 newtons. So the normal force is equal to 49. And remember this problem, we're assuming all the surfaces are frictionless. So there's no friction here, right? Then what? Then there's a tension T this way. And then what does that do? And then there's no other friction force this way. So this T makes this guy accelerate forward, right? T is equal to what? 5 times its acceleration. What is its acceleration? Let's say A2, you know. And then how about the forces on the 20 kilograms? So these two, this one is the force on this guy, right? Then you got the, you know what? Let's even make it even better. Let's do the forces on this guy in the y direction. So it's better to be more organized. This is the 4 kilogram block. right? Y direction. So from the Y direction you get T is this. Then we need to analyze the X forces on this guy, right? X direction. Right? What is that? Well, the only force on this guy is P. Right? That one is pushing this 4 kilogram this way. P. That's equal to what? 4 times its acceleration, right? Well, whatever acceleration this one has, A2 is going to be the same acceleration as what? Yeah, it's going to accelerate at the same rate as this guy because they're accelerating together, right? So this one is naturally going to be the same acceleration as A1, right? So that's going to be P is equal to 4A1. Then we go to the 5 kilogram block. Y direction, and then with the Y direction, N is equal to 49, right? And then the X direction, you have what? T is equal to what? 5, and then the acceleration here is what? A2. Right? 5A2. So now we go to the 20 kilogram. How about the Y direction of the 20 kilogram? What are the Y forces on the 20 kilogram? Okay. Well, there's the normal force of the ground pushing it up. We can call that N prime. Right? Then there's its weight. 20 times 9.8, 196, right? Then you got the weight of the 5 kilogram, the N, pushing back down on the 20 kilogram, right? Because the 20 kilogram exerts a force on the 5 kilogram up, the 5 kilogram in return exerts a force down, so that's N. So N and N prime. So for the 20 kilogram, N prime is equal to N plus 196, right? But we already know from here that N is 49, right? And so therefore N prime equals 15, 1, 10, 245. So that means this block feels heavier, right? Because there's another block sitting on it. Pretty much that's the idea, is if you have somebody on you, you feel the combined weight of you and it, whoever you're carrying, right?
A question. So if we're moving it at a force where these blocks remain in place, the normal force from the 4K isn't added to the total?
Yeah, but on this one, there's no vertical normal force. There's just tension.
Okay.
Right?
Okay.
There's a horizontal normal force, and we're calling that P.
Okay.
Yeah.
Oh, that's right. Because I dropped.
Yeah.
Yeah.
And then the X direction forces, well, for the 20 kilogram, are going to be what? F, right? Minus the P. Because when this guy pushes on this guy in return pushes on this guy, right? So we have here F minus P is equal to what? 20A1. Okay? So now we can go to answering the question. The question is, what should the force be that you push 20 kilogram? What should that be so that this and this don't slide down and this doesn't slide this way? Right? So then what's going to happen? If this guy is not sliding this way, it literally means that the A2 is equal to the A1, right? If their accelerations are the same, then to someone sitting on the rest frame of the Earth, it's going to look like they're accelerating together. You see? And then that way, this guy is not going to accelerate down at all. They're just going to go like this. And then this guy is going to accelerate only this way. Right? So that means A2 must equal A1 in order for this system to look like they're stationary. Right? So if A2 equals A1, what's going to happen? Let's see here. Here we already know the tension is 39.2. Right? How did we know that? Because if the tension is 39.2, that means this guy is staying in place. You see, standing in place. So what happens? If the tension is 39.2, we can put that here and we can calculate what A2 is. In other words, if the tension in the string is 39.2 newtons, that means the acceleration A2 of the 5 kilogram block is going to be 39.2 divided by 5. You see? So what's that going to be? 7.4284, right? So now, how can I fine-tune the acceleration A1 so that it's also equal to 7.84? You see?
By adding force.
Right? So then I'm going to put here A1 is equal to 7.84. That means I can calculate what the P has to be. Right? So in other words, the fact that the 4 kilogram is stationary sets a limit on what A2 has to be. Right? And then that sets a limit on what the P has to be. Right? So then that's going to be 16, 1, 32, 33. And then once you have a limit on the P, you put it here, and then you get the F, right? Then what's the A1? Well, the A1 is equal to 7.84. Yeah? 188? So you have to exert 188 newtons? Did I do the math right?
Yeah, that's what I said.
So you exert 188 newtons here. That's enough force for this guy to push this one ahead so that it accelerates forward. So how is that? How is the physics of that working? When you push this guy ahead, this guy's accelerating and this guy's touching this, this guy's pushing on this, such that the force P is equal to 31.
I think it's because it's falling. You just move it as fast as it's falling, so that way.
Yeah, I'm trying to see the sequence of events that are going to happen when you push on the big block, so that we can kind of trace the steps to see what's happening that's keeping this in place. You see? So you're exerting a force on this guy, which is making this guy go and push this one. And then this one is pushing it with a force of 31. Right?
P.
Oh, okay. You know, this P has nothing to do with how the acceleration of this guy up and down.
No.
That has to do with the makeup of these two weights.
Right.
You see? So with these two weights, what's going to happen is that you got the weight, which is 39.2, right? You got the tension and this. So what that means is, if the gravity is equal to the tension, as they're equal, then the tension will equal 39.2.
Yeah.
Which will make this guy accelerate forward.
Otherwise, the bottom block would just.
In other words, if you didn't push on this guy at all, if it was just a table, this guy would accelerate down. Right? Would actually accelerate down.
Well, if it wasn't tied, if the 5K block wasn't tied to the other one, when you push the bottom block in the frictionless setting, the block would stay in place and drop.
Which one? This one?
The 5K.
Oh yeah,
If
exactly.
there was, so because that's not doing that because it's tied to the other one, that force is what's keeping the block up. Because otherwise it wants to stay in place, right? And we're pushing the bottom block, so that tension is keeping the 4K block from hitting the ground.
Okay, so here's what's happening here. If you exert enough of a force on the 20 kilogram, the inertia of the 5 that wants to say, I just want to stay in place, right, and not accelerate, but this guy's saying, no, you're not going to stay in place. I'm going to make you accelerate, right, you see? But this guy's saying, no, I don't want to accelerate. So if you exert enough force on this guy, you can kind of help the 5 kilogram so that he won't accelerate as fast as this guy would have liked. You see that? That's literally the wording of what's happening here. You pushing on this guy is helping this guy so that this guy doesn't have its free will.
Yeah.
Right? Otherwise, if this guy had its will, it would make this guy accelerate even faster. Right? So now we can ask question C. What if F is 188.16 plus or minus 30 newtons? What happens? So remember, A is we've skipped. So what if I exert 30 more newtons than this or 30 less newtons than that? Okay? So what happens? If I exert 30 more newtons than that, I'm going to help this guy even more, the 5 kilogram, right? So its inertia of saying, I want to stay where I am, is going to win out. So it's actually going to look like this is going up. Right? Weird, huh? So how do we proceed now? Well, now that you know this, let's say we do the plus 30, right? So then we go C F equals C 218.16. So once you know the F, you can kind of start working backwards. You can say F is 218 minus P is 20A1. This one doesn't change. It's still the same equation. Is this still true? T is 5A2. Yeah, that's still true, right? So we're starting to accumulate all our equations.
So the only thing that isn't true is A2 equals A1?
Yeah, the only thing is not true is A1 is A2, yeah. Then this one, this is still true? P is 4A1. Yeah, that's also true. So how many unknowns do I have here? 1, A1, A2, P, and T. I have 4 unknowns, right? P, T, A1, A2. So I need 4 equations. Did I have 4 equations here? Yeah, here's my first equation. Here was my second equation. Here was my third equation. And here was my fourth equation. Right? So I need now my first equation. But this is no longer true, right? if you're pushing larger than that, what's going to happen? This isn't going to stay in place, right? It's actually going to start accelerating up with an acceleration of what? Let's see, we got here A1. Oh, you know what? This is going to accelerate up with an acceleration A2. This is still A1. So it's still true this guy accelerates this way at acceleration A1, right? But it accelerates now up with an acceleration A2. Then what happens to this one? No, you know what? Hold on. It still accelerates down with an acceleration. The acceleration is down. It's A2. This one is equal to A2. You got 39.2. Yeah, I believe it should be, let's see here, T is equal, hold on, T is equal to 5A2. Yeah, that's still true, T is 5A2. Did I write that? T is 5A2. Then you got P is 4A1. That's true. Okay, here's the fourth equation. 39.2 minus T is 4A2. Right? So in other words, instead of saying T equals 39.2, because they're no longer the same. So now 39.2 minus the T is equal to 4A2. Right? Remember before, this guy was staying in place. Right? Standing in place. So this one was 0, and then T was equal to 39.2. Okay, now let's see if we solve this, what would we get here? Okay, if I get P is 4A1, I can substitute into here, right? Okay, so and then how do I get and then I can take the T, put it into here. It's almost like these two are independent and these two are independent. You know? So you can take this, substitute into here. And A2 is going to equal 39.2 divided by 9, right? So what's happening? Is this still falling down? Is it a bit confusing? I think what makes this problem confusing is reference frames. You got something on top of something else, and they're both accelerating at different rates, right? So this guy is accelerating down. This guy is accelerating to the right at this rate. right? But this whole system is moving to the right at that rate. The way to best visualize it is almost take different snapshots of this system every 1 second interval and see what the picture would look like. And then maybe from there you could imagine you draw something like this. Let's say this is 10 meters long, and then this is, let's say, the block starts out here. This is 2 meters long. And let's say from here to here is 6 meters long. And let's say from here to here is 4 meters long. Okay? So after pushing this with a force of 218, after 1 second, where will everything be? 1 second later, where will the block be? Where will this guy be? Where will that one be? Then 1 second later, where will they be? 1 second later, where will they be? And you can have a computer generate this. And then you can actually see, oh, really, now I understand what's going to happen, right? So 1 second later, what's going to happen? How far will the block have traveled? Well, the big block is moving forward with an acceleration of 9.09, right? So 1 second later, what happens? Right? So now you use kinematics. Then here you put 4.5, something like that. So that means the front of the block will have moved by 4.45 feet, so it'll be somewhere here. Let's do a different color. So then this one will have moved here. This one will have moved there. Okay, now where will this guy be? Where will this one be? It's accelerating down by, let's see here. That's the A2, right? $2.178. So that means it's gone down 2.178, so almost halfway to the ground now already, right? Now the crucial thing is, where's the 5 kilogram? How long was my string, by the way? My string was, if this one was 4 and this was 6.
Move it to the right, 2.17.
So this one was, looks like it's about 2. Well, imagine that the blocks don't have any dimensions, you know. So from here to here, let's say would be what, 2 meters, right? And this is 2, so the string is 4 meters. Oh no, that's not good. I need to make the string longer, huh? Because this one will have gone over here, right?
By 1.78.
So let's make this one longer. Let's say. So from here to here is 2 meters. And from there to there is 6 meters, right? So the string is 8 meters, let's say. Length of the string, 8 meters. So once you decide where this block is, the location of the other block is limited by the length of the string, right? So then you can say, okay, the other block is, if this one went down, how much did it go down? It went down, well, originally it was 2, and then it went down by 2.178, so its length is now 4.178 from the top, right? So then what's this length now? Total length is 8 meters, so 8 minus 4 point,
2.822.
so 3 point, so it's 3.822 meters from here, right? Oh, that went down very 3 point. So about. Oh, it's now closer to this end.
Would it still be one left?
Huh?
Would it still be one left? So do you just want
Isn't it? Hold on. 3 point. Let's see. 8 minus 4. That's 3.8. Isn't that more closer to the right side? 6 plus 2 is.
I guess it's the bottom moves too.
Huh?
I guess it's the bottom moves too. So like, yeah, relative to the 20 kilometer or kg block, it's going to be 3.8. But the 20 kg block moves as well. So
Yeah, that's the next thing I'm going to ask. We're relative to the bottom. Let's see here.
Well, we're doing it off the string length.
Well, I'm doing it off the string length.
Yeah,
so if this one was 2 and 6, so then I'm saying if this one now is 4.178, and then the length of the string is 8, 8 minus this is 3.822. So the block is closer to the right end now, right? So according to someone on the ground, how much has the block moved? According to a ground observer.
which block?
The top block.
Okay.
Relative to
Yeah,
block or
relative to
us?
relative to ground observer. He was
You just add A1 and add A2 and then just consider that the acceleration.
4.55 plus.
let's see, from here to here was what?
It'd be
So you just add
4.55
A1 and
plus
A2 there.
3.8.
This one was from here to here was what? 2.178.
Right.
Oh, you know what? I think I should draw this a little bit more like this. So the right end moved over there. Let's see here.
Then why are we using that number to calculate the block on the string? That was the y coordinate, Jackson.
Huh?
Yeah, I know that's
Wasn't
right.
it the
It's
white
6.723. If you consider like the box, the 5 kilogram box itself, and acceleration 1 and 2, just add them together and do the kinematics, it moves 6.72. But if you
How are you
just-
getting 6.72?
Okay, so you take 6, you subtract 3.822, and then you add 4.55.
Where's 4.55?
That's the translation of the 20 kilometer box.
Yeah,
Or
that's
kg
how
box.
far the block moved.
You found it over
Where
there.
did I find that?
It's
Right
the
there,
black
like,
one.
blue
I think I've erased it.
No, it's right
It's
there.
4.55 in the black.
Right down to the left.
Half 9.
Oh, I totally forgot about that.
But
So you add that
blue,
to
the y coordinate, not the x.
So this one was the movement of what?
Of the big box, the one on the
Yeah.
bottom.
Oh, okay, so that's what I was doing wrong. So the block moved by 4.1,
5.5 meters.
then what? Let's see. Okay,
You have to do
yeah.
4 minus 2, or 6 minus 3.822, which is the same thing.
when you add 4.55 to 3.82, because
No, it's the difference. It's the
I know,
change.
but it's moving further along the block to the right.
Yeah, so you do 6
And the
minus
block's
3.
also moving 4.5, so they're both moving
Yeah,
in the
but,
right
but
direction.
if you consider the block as one thing and the boxes on the block as another thing, you can just add them together to get the position from the viewer. So on the block, it's moved a total of 6 minus 3.822 feet. Or
No,
4
that's the
minus
total length of the
4.17.
string is 6. It moved to the right
The total length of the string is
3.822.
8. It moved the string moved by a unit of 2.178, which is 4.178 minus 2, or 6
So
minus
it's 2.178 plus 4.55.
4.55 plus 6 minus 3.822, or 4.55 plus 4.178 minus 2.
Why are we adding 6?
We were not. Oh,
Maybe.
I added 6 to subtract 3.822, which is how much the block moved on the block.
Okay. Because we have that other number.
And if you do the other way, if
Well, 'cause the other number where it dropped will tell you
Maybe
how far it
maybe
moved
the
to the
picture
right.
should look like this.
And
more
then you could
correctly,
add that to 4.5.
or-
you could do it this way, or you could do it by
Yeah.
adding the acceleration of
Yeah.
both, and then
Because
doing
you got
half
the
each.
3.822, but figuring out how much that other block dropped down.
Yeah.
So that's the number I was using, and I was adding that one
But okay,
to the 4.55.
so in the black picture, it's 6 from the edge, right? And then from the second one, it's 3.822 from the edge down. So how far did the block move on the box?
Yeah, but he got that number from he erased it now, but it was at 2.18. I don't remember.
I mean 6 minus 3.
So basically, however much the
Yeah, that's how much the block on the bottom moved, which is how much it moved.
how much
the
this
one on top.
block dropped is how far this block moved to the right, and you add that
Yeah,
to
and
the,
you
the
add it to
length,
4.55.
total block moved to the right. But yeah,
That's the same.
it just depends on like which numbers you're using, because yeah, I get what you're saying. Yeah.
But if you don't want to do it this way, you can just add A1 to A2 and
Yeah.
do half A2 squared.
This one was what? 4.178.
It just threw me off because we were using the 6, and I was like, we already had this number. Why are we?
Like that, right?
Yeah.
So now the distance that the block moves, someone from the outside will say, keep the XY axis here from here to here. What's that distance?
I mean, you have to move the XY axis there too. If you want to do that.
Huh?
You can't do it like that because then you move the origin when you move the.
Well,
No, I mean keep the origin here. Let's say the location here, and say
however much it moved to the right would be how much the blocks fall.
so. The distance from
Like on
oh,
top.
so what you're gonna do is to say
Figure out.
6 plus 4.55
No.
minus the 3.822.
Exactly.
Yeah.
Yeah.
That's from the image. Yeah, exactly. I wanted to show the picture of that.
Oh, okay.
So you can say, okay, what's the distance from here to the center of this? Well, it's 6 plus this minus that.
Okay. Now I see where we're reading this.
So what would that be? 10, about 7 something? Oh, what is that?
6.728.
Oh, 6.728 meters. So that means the distance of the block with respect to the ground. So it moved forward. How about with respect to someone, let's say, riding on the top of the block? Let's say on the top of the block, next to the block. So then where would that guy be? Well, that guy would be 4.55 meters ahead, right?
Yeah.
So someone riding with the block's reference frame, how much did the block move?
6 minus 3 point.
Then it just be what?
2.178.
Yeah.
So x from the block's reference. So then it's going to be this minus the 4.55, right?
Yeah.
right? Because you're moving with the block. So according to the block, the top block moved less.
Yeah.
So you subtract this portion off, and then you get what?
2.178.
So that means in this system, if you're exerting too much force, it's still, even if you're riding on the block, it still looks like it's going forward.
Yeah. And the X block reference was also the number.
The block is still ahead of you, huh?
I mean, it's following.
In other words,
down.
you've gone 4.55, but the block is now ahead. Can we create a scenario where the block is actually, you're going faster than the block?
If you get the guy to move on top of the
No. Just resting on the block. In other words, if I exert more and more and more force, can I have a situation where this is going like this and this is actually going up?
Oh.
I don't know how fast. How would we figure that out?
In other words, I would have to make the PF so large, right?
So, in equations, what will we trying to make it? Or
In other words, find the limit of this as f goes to infinity, kind of. I don't think we could, because even though I had 30 newtons, in other words, when the F was 218, this thing was stationary with you, right? And so if you were riding along with it, you would see it next to you. When I made the F 218 larger, right?
why would more force?
Huh?
Why would more force? Like, if a certain amount of force kept it in place, how come more force would cause it to go forward?
Well, so the amount of force we put on would only affect A1, right? So how is that gonna mess up A2 to go the other way? I don't know. Because the force we apply.
The force you apply is affecting the A1.
But how is that going to affect A2 to get A2 to move the other way? Because the only forces working on the blocks in the pulley system are tension and what's it called, and gravity in the direction of the string.
Right.
Or in other words, you're saying the value of the A2 is kind of set in place. Right?
Because it's you're moving in like a perpendicular direction, so I don't think you can affect it in any way.
What were the two accelerations we got? A1 and A2 in this case?
A1 equals 9.09, A2 equals 4.355.
Could we have predicted this result
Yeah, if you added both of them,
if you subtract the two accelerations, right?
No, you add because they're going the same way.
No, I think we should subtract. If I want to say the acceleration of this block with respect to this, I should subtract them. So A1 minus A2, it should be 4. In other words, this is the acceleration A1 of this block with respect to the ground. That's the acceleration of this guy, right, with respect to us. So now if you subtract 4.64, so now you say the distance, it goes 1/2 4.64 t squared, right?
It's close. It's like 25%.
No, it should work. It's because it's the acceleration of one with respect to the other. You see? Now, I don't think we can create a situation where this will actually accelerate back with this system. Okay, how about if the force is 30 newtons less? What changes? Okay, well again, you've got, this thing is, let's see, you've got the 4 equations again. So you got this one is 155.16 minus P is equal to 20A1. This one is still T is equal to 5A2. And then this one is still P is equal to 4A1. And then the other one is still you know what? A2 is not changing, just like what Jasper was saying. This is independent of these two, right? So A2 is still coming out to be 4.35, right? Is that what it was? But now A1 is changing, which is the acceleration of the block, of the big block. So now you're going to have your P substituted into here. And then now that should be smaller, right?
Yeah.
What is it?
6.59.
6.59. So instead of being something seems weird, because if 188 gave us the two accelerations were the same, and if I'm bigger or smaller, shouldn't I get once the acceleration A1 is less than A2 and the other one A?
Yeah.
I think, are we calculating something wrong?
For force, we subtracted the 30 and divided it with 155 instead of
158. I mean, yeah, 158. But something is wrong with our calculation, because if I add 30, when at 188 the two accelerations were the same, how can I add 30 and subtract 30, and both times A1 is larger than A2? Then what happens at 188? Something is wrong with our calculation, I think.
Well, isn't no, it's frictionless.
Was that answer 188 correct?
We erased the board a couple times.
Yeah. You don't have it there?
Yeah, I do.
I mean, the only thing we did for 188 was we assumed A1 equals A2.
Why wouldn't A1 wait? Wouldn't A1? Wait a second. Why would A1 equal A2? Wouldn't it equal?
Together, A1 equals
Would it equal 2? Because it's frictionless. So the block on top is on a frictionless. So the
They're all frictionless.
So it doesn't have the acceleration of block going this way, because the block's just sliding out from under it, right? So the acceleration of the 5K block would just be the tension of the 4K dropping, right?
Yes.
So that would be A2. So why would A2 equal A1? I guess that's how we figure out if it stay the same.
I think A2 equals A1 because that term of reference.
That's when it doesn't.
That's when it just stays
doesn't
together.
move, right?
Yeah, they both stay together. Yeah.
Then outside of that situation, let's see. Okay, so there should be a way then for it to accelerate enough for it to go backwards. Or because it's frictionless, maybe it doesn't matter at all because that's just gonna do whatever it's. Well, it's frictionless. The 4K one will go up and down regardless of whatever horizontal force is applied to it. And since the 5K has no,
I think it's because one of the principles one of the 4 equations we found in the ladder cube, something has to be wrong. So
yeah.
I'm just a little.
What I'm saying is, how fast the 4K drops is not affected by how much force is going to the right. That doesn't affect the speed at which it's dropping at all. And since the one at 5K on top is on a frictionless surface, it's not affected by the acceleration of the 20K block. So then it's almost irrelevant how fast it's going to the right. It's kind of just going to fall at the same speed because isn't that the way it works? Free fall? Like if you hit a marble sideways, it's still going to fall at the same speed no matter how much it's going to the right. It's like a person who did physical, right? I think it's because it's friction this is different than most.
I mean, the thing about our numbers is like one of them's above double A2 and one of them's below double A2. So maybe that has something.
Well, like what I'm saying is, we were always assuming the force going to the right was going to affect anything, but I don't think it does because the horizontal force doesn't affect the vertical
Yeah, no, because
at all on the 4K, right?
But the thing is, our equations equations predicted that. Those two of the equations were not.
But like since the 5K is on a frictionless surface, the acceleration at the bottom one isn't affecting the top one.
Yes. A2, A total is equal to A2 plus A1.
And this has to be a double. Okay. Thank God. So then that way, when it was 9.9, it would go faster and it would go to the right.
Okay. There's a total acceleration here because it's riding on this.
Oh, because it's still
This one
tied
has
around
acceleration.
So that's why double A2.
Like, even though I'm saying it's not connected, it is connected around the pulley. So
this is when it's exciting.
It is adding both.
You just work your way. Okay. You talk about these things, and of course, all of that was orchestrated and staged. I knew this all along, right? I don't know. You tell me. Maybe I knew it. I was faking it. But yeah, it's awesome. I love that. Yes. So the equations is A total is A2 plus A1. So does that change our first answer then? I think it changes everything. Huh?
Yeah, I think we have to start all over.
So let's go back to what happened. What changes then? T is 4A1. I think that's I think that's okay. That one stays. That's the same. So I'm gonna come up with our 4 equations so that once we do that, we can solve it for all of them. Yes. So for this guy, T is 4A1. For this guy, is 39.2 minus T is equal to what? 4A2. For this guy, is T is equal to 5A1 plus A2. That's what I had wrong. I had it 5A2, right? So that's the one where you have to add. And then for this guy is F minus P is 20A1. Yeah. So now, if we want to answer question B again, right? So then what do I want if that's the case? Then I want the A2 to be 0, right? Set A2 0. And that means this is 0, this is 0, right? And then T is 5A1. Yeah, that makes sense. Oh, so good. So P is equal to 4A1. T is equal to 39.2. T is equal to 5A1. F minus P is equal to 20A1. So F is equal to 24A1. Right?
That's it.
So if T is 39.2, we can solve for A1 from there. Oh, that's the same answer, huh? I think that's the same answer. I don't think it's changing.
No, I think your answers are right because the thing is, I noticed this before, but one of the answers was greater than double A2, and one of the answers
Yeah,
was less than.
when you said that, something clicked in my mind. So I said, oh, I forgot to add A2. So that's why you study in study groups. Somebody says something and then something clicks. See, this is all orchestrated now. It's just, this is the way you do it.
For you to.
So don't panic. 24 times 7.84. Yeah, same answer. So the answer is not changing. But now it's going to change when I add 30 and subtract 30. Right? So now when I have 216, if I have 218.16 minus P is equal to 20A1, T is equal to 5A1 plus 5A2. 39.2 minus T is equal to 4A2. T is equal to 4A1. So now put this together. Right? So change the F to whatever F you want. And then solve all four equations again. So now substitute this here. Okay, so you see A1 is higher than this case. So that means you're pushing it so hard that this block is accelerating fast. So if that's the case, what's happening to the tension? Let's see here. 39.2 minus T. What if I add these two equations? I mean, I can substitute that into here. Right? I have 39.2 minus 5A1 plus 5A2, 4A2. And take these to the other side. Right? So 5A2 goes over here, it becomes 9A2. Then you substitute that over here. Oh, so beautiful. I love this problem. Yeah. Right? Which is what you wanted to say. It should be moving up, right?
Yeah.
So that means A2 is this way. This guy is this way. Oh, yeah? Yeah. Right? And then, is that it? Yeah, that's pretty much solves it. So the total acceleration of this with respect to the ground is still positive, right? But with respect to someone on the table, this is sliding back. Right? You're moving along, but then this is sliding back behind you, and it's still eventually going to fall off. But someone on the ground sees A2 plus A1, right? So the ground person says, oh no, you're not negative, you're still moving forward, right? It's kind of like when you have something in your truck, like a U-Haul, you're driving it, and then you didn't put good carpets. They're all sliding back, but that doesn't mean they're moving backwards. They're still moving forward with you. But with respect to your truck, they're moving back and they're going to hit the back of the truck, right?
Right.
It's like that. Good problem. And of course, the opposite will happen when you have when you put 215. When you subtract 30, right? It's just a matter of now changing it to 158, and then resolving it. But then it's going to come out positive, right? It's going to fall downward. Cool. So the one link was trying to realize, oh, okay, this is when you add accelerations. During the SI, maybe you can solve this one, and I have the video of it. Last semester, I think I put it on test 2. Very few people got it. I have a block on a block. And all surfaces are frictionless. So see if you can solve it before looking at my video. This guy is accelerating down, this guy is accelerating back. And last semester it was on, I put it on test 2.
Is there friction?
No friction. And then each one, you can do the same, but the ideas are similar to what we just did, right? It's like one thing riding on another, and they're both accelerating.
Did you give the angle or?
Yeah, I mean, you can give any angle you want. Okay, now let's start friction. Static friction, kinetic friction. So as I said before, when you introduce friction, you introduce this element of uncertainty. If the object is moving, then the only friction force on it is kinetic. If the object is standing still and somebody is trying to move it, but it still hasn't moved, then the force on it is static friction, but you don't know if static friction is equal to its maximum value or not. It's only equal to its maximum value when the object is on the verge of moving, right? So if I have my calculator here, the friction force on it is 0 because I'm not trying to move it, right? As soon as I incline the table, then the gravity is trying to move it, so the friction force starts to increase. It starts to increase, but it's still not equal to mu Sn, right? Increase. It's still not equal to mu Sn, because why? I know it's not sliding yet. Right? So when it's like 40, 50 degrees, then the friction force is, at that instant, it's equal to mu Sn. But then once it moves, it reverts to kinetic friction. Okay? So once it moves, it goes mu Kn. So the difference is that mu S is usually larger or equal to mu K. This is called coefficient of static friction. You see? So friction has to do with the atomic nature, the electromagnetic force of the surfaces, you see? And on the microscopic scale, if you blow up the surface between the block and the table, you see it has unevenness. That's kind of what's creating the friction. And on top, the molecular structure of the atoms there, right? So if you find that a 50 Newton force is required to move a 100 Newton object, then the coefficient of friction is 50 over 100, right? It's so it's equal to what? 50 Newton, and then the normal force is 100. Right? So 0.5. So then it says here, in motion at constant speed, 40 newtons is required to move the same thing with constant speed, right? Once it moves. So usually there's going to be less force required to keep it moving than to make it move, right? So now then you say 40 is equal to mu k times 100, so mu k is 0.4. You see, so when you first started this class, I threatened you with threats. You don't want to, I said you don't want to drop the first test. The first test is the easiest. But because of static friction, you said, don't worry about it. I'll just wait out the first test. I don't need to study a lot because every other teacher threatens me. And the threat is just empty threat, right? So static friction, that means it took a lot of force for me to make you move. Then test one comes, you know, it makes you move. Now it takes less threats on me to say study, you know. Because now we're in the kinetic realm. We're like, okay, you guys are already moving. Like, okay, guys, second test is going to get harder, but I don't have to yell anymore. Right? And then after that, you're moving even faster. By the third test, I just say, don't even study, man. Don't even, I'm like opposite. You know, I'm trying, you say, guys, let's go out, just drink, you know. At that point, you're the one saying, no, man, I've seen your tests. Right? Okay, good. Now, how much force would require to move the same thing, to make it move, if it was sitting on an inclined plane at 30 degrees? Well, if it's the same surface, the mu s and the mu k wouldn't change, right? So if it's 30 degrees, you're trying to make it move, right? What would happen here? Then you're going to have to, so now you have to worry about two things, the friction force and its weight. Let's see here. Let's draw a nice picture. Let's make the angle a little bit less. Let's say, let's say the angle is 10 degrees. So it weighs, what did it weigh? 100 newtons. So what are the forces here? We got the normal force, we got the weight. The weight is the 100 newtons, right? Then we got the what? Remember, you break down the forces. This is 10 degrees. So this is 100 cosine 10. This one is 100 sine 10, right? Then which direction is the friction force? Up this way, right?
Yeah.
What is it equal to? Well, I don't know. You can't say mu Sn unless you tell me what's happening to the problem. You can't say what the friction is equal to. So you say the friction can possibly equal at most mu Sn, right? So Fs most is mu Sn, right? Now what's mu s? Well, we've already established mu s is 0.5 by pushing it at 50 on the horizontal surface, and we notice that it moved. So mu s doesn't change now, right? 0.5. What's n? Now when it's on an incline, n changes. It's no longer 100, right? the normal force is 100 cosine 10. So what does that do? That decreases the amount of total friction on this object, the total friction force potential. You see, it decreases that potential. So it's 100 cosine 10. So that's going to be 50 cosine 10. Okay? So what is that going to be? Okay, it's not too much difference, 49.24. Right? So now, what should I push with so that I make this move? So that I start to make it move up the hill. Right? So now I have to overcome this, let's see here. Friction force is usually. Oh, hold on. Something interesting happens. So originally, this friction force. Oh, hold on. Let me just back up. So this is only giving you the maximum possible friction force on the block, right?
Right.
So now, when you actually get to this situation and you say, what's the friction force equal to this case? Well, 100 sine of 10. What is that? $17.365. So this guy is 17.365. So, can this friction prevent that from moving? Right? Because this is the most possible friction that you can have when that block is on that incline. You see? So 49.24, yeah, that's enough to prevent this from moving. Now if I ask what's the actual friction force, the actual friction force does not have to equal that.
Right.
You see? It's only equal to this. Because if it was equal to that, what would happen? You would put a block on a table and by itself it would move up the table.
Mm-hmm.
Right? That'd be weird. There's a ghost in this table, right? Imagine I did this and the calculator moved up. That never happens.
Like,
So that means this is the maximum when it needs to equal that, right? So now if I come along, and start to push in this, depends on which direction I push. If I push in this direction, what's the maximum force I need to make it move? If I'm pushing down. As I start to push, this guy keeps increasing, right? And the maximum possible that it can equal is what? 49.24. So now I need to increase my force so that this plus this, right, equals 49. Right? So if I want to take that same block and make it move on an incline down the incline, how much force do I need to exert? F plus this is to make the block move down the incline. See what happens? How much harder it gets when you add friction, and then when you add the block and put it on an incline. You see? Because now you have to worry about the component of the weight. You have to worry about the fact that the normal force changes. You know. So now the force required to move becomes this minus this, right? 49.24. Which is less force required than here. You see, on the flat, it doesn't matter which direction you push. It still requires 50 newtons of force. But this one, to push it down to move it down the incline, it only requires 31, so it's easier than flat. Okay, how about up the incline? To move down incline. How about up the incline? So now your force is this way, right? So now what happens to the direction of the friction now? Yeah, see, that's the other trick with friction, is that it now changes the direction. It goes, oh, okay, you're changing direction on me, now I'm going to go down. And what's the most it can equal? 49 still, right? So now to move it up the incline, what do you have to make your force? 49 plus the 17. You see? So F required to move up incline. 49.24 plus the 17. Even though this example I'm doing is not too hard, but conceptually trying to understand and do it is not that easy, and trying to really understand what's going on. So we got here 5, 10, 1, 3, 6, 16, 1, 5, 6. It's 66 newtons to move it up the incline. Well, now that's more than the flat surface, right? So to move the same block up the incline is harder than down the incline. So it makes sense. Now, if I change the angle of the incline to 20, what's going to happen? Now what changes? So this becomes 20, this becomes 20. Do I have to redo this?
Yeah.
Oh, yeah. Now you have to say, oh, okay, the most possible friction you can have is now going to go down. The most possible friction you can have is 0.500 cos 20. So this number goes down now, right? 0.500 times 20 cosine 46.98. So then this number goes to 46.98, right? But then what happens to this number, the 17.365? That's 100 sine of 20 now, right? So now that number increases. You see? So 100 times 20 sine 34.20. So you see, when the incline is getting larger, two things is happening. You have now less friction because the normal force is getting smaller, 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 right? And more weight is trying to make you go down. So now this is 34. Also now the force required to move it down the incline is only like 12 newtons. 12 newtons. I'm just rounding it here. See? You only need 12 newtons of force to move it down the hill. But now the force to move it to required up the hill, then you're going to change that to 46 plus 34. Now it's going to be really hard to move it up the incline. 47 plus 34 rounds up to what? 81? When I was young, I was so much into working out, especially heavy weights. I had two younger cousins who would go on a not steep hill, but like a hill about 20 degrees, similar to this. I would put my car on neutral and they were both inside. I would go to the back of the car and push it up the hill. It's a good workout. It's like what linemen do, basically. You push heavy things up the hill, especially up the hill, because you're not only fighting against friction, but you're fighting against the downward component of the weight of that car. And I would push that up about 30 feet, 40 feet, you know. Now if I try that, I'll blow out my knees. I've got the strength, but the old age, terrible. See, so now I can do it at 30, I can do it at 40. So this example gives you the idea that even though mu-s and mu-k aren't changing, the n is changing. And then the amount of force is changing. Now we're going to do a good problem with it. This guy gives you the coefficient of static friction between the two surfaces. So materials and material combinations, like the aluminum block sitting on an aluminum surface. The coefficient of static friction, if it's clean and it's dry, 1.05. Lubricated and greasy, 0.3. So you see, we went down quite a bit. And that's just mu-s, right? And then aluminum on bronze. Aluminum bronze sitting on a steel surface. Then it's 0.45. Aluminum on mild steel, 0.4, 0.2. So you can see brass on steel, 0.35. But if it's greasy and lubricated, 0.19. So you see it goes down quite a bit. So this is static friction. How about kinetic? They give us a kinetic option. This website is really good. The Engineering Toolbox website. Coefficient of no values. Usually you get a table, coefficient of static and kinetic friction. Okay, this one is a little table. Steel on steel, mu-s is 0.74, kinetic 0.57, glass on glass. But you notice also, if the object is already moving, mu-k is smaller than the mu-s. See? But there are some exceptions, like Teflon on Teflon 0.04, 0.04, metal on metal 0.15, glass on glass. So that means once something is moving, it's easier to keep it moving at constant speed, right? Because you overcome those electromagnetic forces of attraction.
That's why they say Teflon's a non-stick coating.
Oh, it says, yeah?
Well, that's what Teflon is, non-stick coating on like frying pan.
Oh, yeah.
That's why.
So that means mu-s and mu-k are the same and they're both low.
Yeah, very.
Right? Yeah. Okay, now let's do something like this. Let's say this one is 6 kilograms. Let's say this is So steel, aluminum, bronze, 40 degrees. This is 35 degrees. Then I need to say, give you the static friction, right? So aluminum on steel. The other website was more complete, huh? Let me see. Trying to get the numbers here. The aluminum on steel, let's say that's 0.45. And let's say the BK is 0.30. And then bronze on steel would be your 0.16. And then the μk would be, let's say, 0.10. So I can ask this question: is the system going to move? And then if it's going to move, what is its acceleration? Right? So we don't know even if it's going to move. It might just stay in place. So what should I do to determine that? So maybe what we can do is say, well, what's the components of this weight, right? This is 49 newtons. So this one is 49 sine of 40, right? This is 49 cosine 40. And then this is n prime. This is 6 times 9.8, 78.8. Oh, that's 4. No, 58.8, right? And then this is going to be and then got the tension here. We got the tension here. Let's first see which of the weights is larger, 49 sine 40 or 58.8 sine 35, right? Then that will determine which direction the system wants to go, right? So 58.8 sine 35 is 33.73, and then 49 sine 40 is of course the system isn't going to move. It's only 2 newtons difference. That one is obvious. Right? Huh? Yeah, I'm gonna have to make their weights different, right? Because if their weights are about the same and their angles are about the same, then it becomes the system doesn't move. It becomes too obvious that the system doesn't move, and the teacher will never give you an obvious case like that, right? I know him. So we'll make this guy, let's say 16 kilograms. Let's see what that does. So this becomes now 156.8. Okay, now it's not as obvious if it's going to move because this guy is trying to pull down at 89. This guy is trying to pull the other way at 31. Well, the difference is about 60 something. So then what has to happen in order for the system not to move? Right? There needs to be enough friction, right? So if this guy is trying to go down, this guy is trying to go up, what's the friction this way? Mu s prime n prime. And the friction this way, right, is going to be mu s n. That means that the maximum possible frictions that you can have on each one, you see, what are they equal to? This is the maximum possible. So what is that? 0.16 times, what's the n? 49 cos 40, right? Oh, only 6 newtons. Okay, what's Fs prime max on that guy? Then you're going to take the mu s, which was 0.45, right? Times what? 156.8 cosine 35. Right? So is there enough friction? Is there enough static friction to prevent the system from moving? Well, the sum of these two frictions, if it's equal to the difference of their weights, well, that's going to be close. We're cutting it close here. Let's see, 50. No, I don't think so. I think it's going to move, right? If you subtract this minus this, ooh, I like that. No, that means it's going to move. System moves, baby. Okay, wait for Monday for answer. So now we're going to have to find the acceleration of the system. So now that we know it's going to move, we revert to kinetic coefficient of friction. Okay? I like that problem. So this one was very close. This is the one that the teacher likely asks, right? It's hard to guess. Okay, guys, work on your lab 5, right? That's the one with all the calculations and good stuff, projectile motion.